in a moment. So Abeer, thank you very much, and it's all yours.
Thank you. Thank you, guys. It's my pleasure to be here. I'm actually not going to tell you about the successes in this field in terms of using speech as a biometric cue for affect, but actually the challenges, because it's still not a solved problem by any means. And I'll show you what the difficulties are, and that it needs a multidisciplinary approach to actually get to some of the answers. So this is my website. All our publications are on the website, and you're welcome to visit us virtually or in person, just in the building next door. So just in case you're not familiar with these representations, this is a waveform of somebody saying 1, 5, and 7. Okay, this is called the time waveform, so it's pressure fluctuations over time. And these are silences before and after. So this person spoke slowly and said those words. So this is what we call the time waveform. And here is what we call a spectrogram, which is a time frequency representation of the same one. So the x-axis here is time, just like the waveform, but the y-axis is actually frequencies, what kind of frequencies are present in the signal. And the redness indicates energy. So the darker red has more energy than the lighter red. So when we process signals, we look at the time frequency profile of these signals to tell us what the word is, what the sound is, who the speaker is, and hopefully the gender and the age and the affect. We would like to get as much information as possible from the signal. So, so this is, if we just zoom in on one point in time of this spectral representation, this is what we call the short time spectrum or the Fourier transform. And it shows us these are harmonics. So the harmonics relate to the pitch. So the pitch, probably Michael will talk more about that, but the pitches varies obviously by gender and by age. So women tend to have higher pitch than men. Women are usually around 200 hertz, men are around 150 or so. Kids are much higher pitch, around 300 hertz. And these are called harmonics, and the spacing between them indicates what the pitch is for that person. Of course, you can change your pitch when you sing, so you can manipulate that. That's the vibration of the vocal cord. So one important information that is conveyed is the pitch of the person and how it changes over time. And another is also the overall envelope of the signal. So again, this is the pitch, the spacing between the harmonics. But there's also the overall envelope, and that's what we call the transfer function. And these bumps that you see here are points of high energy, which are the resonances of your vocal tract. So versus E, the difference between those two for the same person is where these bumps are located. We call them formant frequencies or resonant frequencies of the vocal tract. So again, there are two things which we pay a lot of attention to. One is the pitch, and one is the overall resonances, which tells you what the sound is. And there are other important cues, but these tend to be ones that people focus on a lot when they describe speech signals and their classification. And again, the big bumps, we call them the formats, which are the resonant frequencies. Now, in this picture here, this is a tracing of an X-ray of the same person. Oops, it doesn't show here. There's an X-ray tracing of a person saying ah, e, and oo. Okay, and you can see that the shape of the mouth is different. You can think of the vocal tract as a bunch of organ pipes, and these organ pipes, as they change in dimension and length, the resonances change. So, so this is the actual X-ray tracing, and this is a very simple model of this X-ray tracing, and this is what the model would predict are the resonances of the person. So we have a fairly good understanding of what gesture corresponds to what form and frequency, especially in isolation. The tricky part about speech is we don't talk like that. We don't say T, we say cat. And once you merge sounds together, they influence each other. And that's called co-articulation. So context becomes really important in speech. And that's why it's not an easy problem to identify. If we all spoke like that, like isolated sounds, it would be easy, but we don't. And so even a sound like, if go back to K as in cat, if we say K as in cat and K as in key, the two Ks are actually different. They're not the same because they're heavily influenced by the context. So again, we have these targets, isolated targets, and then we have speech in context, running speech. And so they're different styles of speaking, and they get progressively difficult. So if you are speaking slowly and having pauses like a robot would, then actually that's easier than if I speak like this and just get very fast. My speech and the pauses get all shrunk and the sounds influence each other. So speech style and therefore the emotion could heavily affect what the signal would look like. So that's from what we call the production point of view. That's going from the pipe to the resonances. But speech is meant to be understood and listened. So our ear does very interesting processing of the signal so that we can decode the signal properly. And one of the things it does is our hearing is not in a linear frequency scale, but it's a warped frequency scale. You can think of it as octaves, right? So the way we process low frequencies is different than the way we process high frequencies. So this very simple picture here shows what we call the resolution at different frequencies. So at low frequencies, our resolution is really fine. And then, but at the higher frequencies, our bandwidth increases, so there's less resolution. Okay, so that's the way the ear works. And when we do speech processing, interestingly, we find that if we use properties of the auditory system, we actually get improvements in terms of performance and classification. So speech, you can't deal with speech just like any other signal, just throw it in the machine learning and out comes, the results. You really have to pay attention to how you process the signal in terms of understanding how we produce it and how we perceive it. So it's really a fascinating area, and lots of progress has been made over the years from playing around with these representations. So this is, for example, a normal spectrogram, like linear frequency scale, and this is what the picture looks like after it's being processed by a filter bank, which simulates how the auditory system would hear these sounds. So it's a little different. So I've done a lot of work on these kinds of things in terms of how do you pre-process the signal? How do you do feature extraction so that you focus on the important parts of the signal? Not everything in the signal is equally, or not all segments are equally important. Some are more important than others. Just to give you an example, one of the things, let's say you're taking a picture, you want to take a picture of every person in this room. It's a waste of your time to take a picture of every chair because many chairs are empty. So you would only take, if you were doing it automatically, you only take a picture of the chair when somebody is present in it. And that's the region of interest, right? So the same thing for the auditory system. When there is, for example, some silence here, it doesn't really, do much in terms of listening and trying to classify the signal. But things like dynamic movements, fast and slow, are very important. And we pay more attention to that. So again, one of the important things when you process speech signals is to pay attention to areas which are important, and they tend to be the high frequency, the high energy areas, and dynamic ones. So for example, let's say there is a movement here, and then so it gets steady. This part, the dynamic part, is much more important than the steady part, because the steady part, you can just take 1 point or 2 points, and that represents the line. Whereas a dynamic one, you have to know the slope and where it's coming from where it's going to. So again, there's lots of details to pay attention to in the signal. Some of it we know from our studies on perception and production, and some of it we're still uncovering. So what is the difficulty in speech processing? Variability is the big one, right? So I don't say cat the same way somebody else would because either of gender or accent or age or emotion. So variability necessitates, statistical looks at this data to observe trends and behaviors. But also variability hits us the other way is that when the data is limited or when the data is noisy, data-driven approaches by themselves don't really work. And that's where my research has been over the years. I leave Google and Yahoo and all these companies to areas where they have a ton of data and they can, millions and millions of segments that they can just process by machines and get out the data. I focus more on areas where, what if you don't have enough data? That happens a lot. For example, children's speech. Because of logistics and because of privacy issues, there are no large databases of kids' speech, even though it's incredibly important for applications in education, health, etc. Another one is accents. There's no way you can capture every possible accent of English, no matter how much you try. There's always going to be a surprise. So, and then noise is another one. So you might be, let's say, recording my voice in this room. It's fairly quiet. But when I speak in the car on my cell phone and the windows are down and the kids are screaming in the background, that's noisy data. And it's not going to be the same, okay? So, so that's why we've made a lot of progress in terms of the more, I would say, clean data and the well-behaved data. But when it comes to noisy data, there's just either not enough data or we just don't know how to process it. But again, progress has been made, as you've seen in Siri and other applications. So again, what are the challenges for example, classification in general speech? One is background noise, whether it's acoustic noise or the channel noise. Let's say you're talking to somebody on a cell phone and packets get dropped in a bad reception area. And so there is this effect. And obviously, if you have a machine trying to recognize speech, that's a difficult problem. And also, as I said, robustness to variations due to gender, age, affect, etc., and speaking, right, and limited data. So I'll just highlight a few examples of recent research we've been doing to get at some of these topics, and please feel free to interrupt to ask any questions. So our most recent project is capturing within and across speaker variation and voice quality. What does that mean? That means that, as I said, if the same person is reading aloud versus having a conversation with a stranger versus having a conversation with somebody they know, that's a very different style of speech. Can you guess what's the most difficult style of speech? It's actually talking to somebody in your family or somebody who's very close to you. Because the way, there are databases about the way these conversations go will be like, oh, I went to, oh, the dog is barking. And you know how he is. And then if he ate something, you drop words, you refer to things which only that person knows because they know you very well. And that's the most casual, most difficult conversation to recognize. The easiest is reading aloud. Even broadcast news is not bad. Reporters, what they are reading, what they say. But the interactive style, conversational style tends to be different. So we were intrigued by the question. We wanted to know how people vary in voice quality. So both within speakers and across speakers. So you have different styles of speaking. If I'm listening to the phone to my mother when she has a cold, I can still recognize her, but perhaps a machine won't be able to. Okay, so again, these are just the different emotions and that could affect. So we looked around for databases that could capture this kind of variability. These are some of the famous ones out there, and we realized that they didn't have what we were looking for in terms of the number of speakers, the differences in style, and multiple recording sessions. So in collaboration with the linguistics department and the medical school, and with funding from the National Science Foundation, we have recorded 200 speakers, half male, half female. All were undergraduates here at UCLA. And we recorded them saying different utterances. And so, for example, we changed the time and the time and day of when the speech was recorded, low affect versus high affect speech. Because most of the databases that exist out there, they're usually either actors, which are acting out emotion, or you would have, angry speech, but you don't have a reference for that person. You don't have their speech when they were not angry. So we wanted to have the same speakers, and we induce these affect naturally. So we'll tell them to recount as an incident which made them very happy or very sad. So it was really interesting. So we had different styles, steady state vowels, reading sentences, explain something to someone you don't know, and then making a phone call to someone you know, and speaking to pets. And that was it was really interesting. And the reason why we chose this is because it actually has similarities to how parents speak to their infants. So, if we show them a kitten, they go, "Oh, how cute!" They exaggerate. They're it's adorable. And as we found out, that was actually the hardest speech signal to analyze. The rest we could analyze fairly well, but speaking to pets showed the extreme case of high emotion and squeakiness. So it was a lot of fun to look at this. So we started looking at the data. We're still analyzing it. It will be available to the public soon. And again, motivation was to see how much the same person varied across styles and how much are they different from others. Because you normally think that a person sounds like themselves more than they sound like other people, right? But if you look at the different styles, that's not necessarily the case. So some speakers sound more like other speakers when they're speaking a different style. So it was really interesting to look at that. This is just one example of some of their observations. So the x-axis is the speaker number, speaker ID, and there are females and males. By the way, I should say that unfortunately many of the studies done in speech before have been mostly on male speakers. So I guess in the medical field it's probably the same thing, but we wanted to make sure that we have an equal number because the tendencies could be different. Okay, so these are two parameters. One's called F0, which is the pitch, and the other one is H&R, which is harmonic to noise ratio, which is a measure of jitter and shimmer and fluctuations of the signal. And you can see, for example, in the lower panel for speaker 51 in light blue, she varied a lot more, in her utterances more than when compared to other speakers, meaning that this is the kind of person where you could easily confuse with somebody else, okay? Whereas others have a very tight variance, like, for example, speaker number 43, and most of the time they sounded like themselves. So these are the kinds of things we're looking at. We're looking at what are the features that fluctuate across styles, across genders, and there's a lot of individuality, as you might know. Now, why are we doing this? Again, there are many, many applications, both medical and non-medical. For example, there is a whole area of speaker identification and speaker verification, where you would like to identify the speaker. Let's say you're accessing your phone and you're using your voice, for example, as a voice print. You want to make sure that it is you and not somebody else. And there are many other applications. In health, for example, the person who was collaborating with us on this study in the medical school, they're interested in rehab. So if you do surgery on, say, the vocal cords, and you're trying to do some exercises to make them sound like how they sounded before, before they had the disease. So it has medical, it has law enforcement application, it has just fun communications application, but it's a very important area to look at speakers and how they change. And also it's important for when we do synthesis, when you synthesize speech and we want to make it individual to your own voice. Let's say you want the machine to be talking to you in a voice similar to your own voice, then you can incorporate information from how these parameters change with different styles. So anyway, so we did observe that some speakers do have a large variability, and we also did both a machine classification experiment and a human classification experiment. So basically, we had people come and listen to this data, and they'll rate the similarities between subjects, and we also had a machine do the same thing. And the idea, the hypothesis was that if we incorporate into the machine learning how humans are doing the classification, because speech is meant to be for communicating between humans, then we probably will get better performance. So this is just one set of data, probably a lot here, but this is the accuracy versus different features we get from the signal. So if the matched case, there's a matched case where you recognize the person with the same style. So you train on their voice while they're reading, and you test while they're reading. Okay, so same style. Mismatch means you train in one condition, let's say they're being sad, but you test on a different condition when they're happy. So the mismatch case is a more difficult case, and that's what we encounter in real life situations. So you can see in the matched case, you can do fairly well, let's say, okay, so I have to explain the different features. Vocal tract means you're just capturing the format frequencies and resonances. The voice source means features related to the pitch. Perceptual means features related to how we hear. And MFCCs are the features that people usually use for classification, but also inspired by the auditory system. So there's different sets. So the best performance of these is number 3, right, which has 94% accuracy in 90% accuracy in match and mismatch condition. Okay, some of the features do well in match, but not so well in mismatch, right? But the best one are the perceptual features. That's when the feature extraction emphasizes on how humans are listening to these sounds. And so this is really promising, and we're continuing to do more experiments. One of the students now is working at Johns Hopkins because they have a very big machines which can do these very fast, because this is a lot of data. It takes days to get these experiments, and so we're having even more interesting results. But the bottom line is that if you want to capture the mismatch between training and testing, it's best to use features which emulate how we hear or how we produce. I have 5 more. All right, so that was one project. I'll very quickly tell you about another project. It's also fun. It's estimation of height using what we call subglottal resonance. Okay. So the resonances I talked about before were related to where your tongue is with respect to the jaw. But there's also the subglottal system, which is the bronchi, the lungs. And usually we don't pay attention to resonances from this system. It's usually not even, we don't even worry about them. But some years ago, I ran into a scientist at Harvard Medical School who was looking at the subglottal resonances and was telling me that these resonances are fairly constant. They don't change because, we don't change much in terms of bronchi. Not like the tongue. When we talk, the tongue moves a lot. And so we have different resonances. But the subglottal system is fairly steady. The resonances are the same, whatever you say. And so we have this idea, well, what about, and these resonances are related to, the overall trunk height and overall height. Perhaps these resonances can also be useful in identifying people, right? So again, this is again a picture of the same spectrogram of somebody speaking. The green are the formats I showed you before that change with sound. The red ones are the subglottal resonances. And then you see they don't really change much, no matter what you say. Okay? So they are more a feature of the physiology, and and basically they stay constant. So again, we actually worked with WashU in St. Louis to collect a corpus and recorded. There was no corpus at the time. And recorded people and measured their subglottal resonances and their speech signals as well, and developed algorithms to extract the resonances from a regular speech signal. And we found that actually we can use that information to estimate the height of a person. Now, it's not 100% accurate, it's within 5 centimeters, but the interesting thing is that we're only using 1 or 2 features, which are subglottal. Other people who have done height estimation based on machine learning, they have 50 to 60 features in there. So, so what's interesting is that if you are careful about what you choose as your feature, and it's in a principled way, you could get just as much as thousands of tiles thrown into a machine learning, or maybe even better, when you have features which are important. So this is just a correlation between the resonances and the speaker height, and there's a slightly different equation for children versus adults because we're interested in kids' speech. So anyway, I think I'll stop here. We have many more examples of this. They're all in my slides. This is another one on the noise robust speech recognition. This is speech and noise. And I'm just going to play you really quickly these things.
9, 6, 1.
Did you hear that? Okay, 9, 6, 1. For a machine, that's a very hard signal to recognize if it has not seen this type of noise before. So if it only had recognized you the top one, when you said you trained it on your speech in quiet 961, and then you just have a little bit of noise, the machine performance is horrible. So again, in that area as well, we looked at features which humans are sensitive to in terms of perception and production, and managed to get really good performance with noisy speech. So I think I'll end here, give you my final slide. So we did achieve improved performance for speaker normalization, speaker identification, using subglottal resonances, estimated the height, and also features for the voice qualities. And in terms of noise, the same thing. But we're yet to achieve human performance. And I think this is going to keep me busy until at least I retire. The machines are very good if they have seen examples of the same thing before. But if you change, if it's been trained on your voice when you didn't have a cold and then you have a cold and talk to it, or if you have an accent, talk to it, it hasn't seen that accent, it still doesn't work. Humans do something much more than statistical analysis. They extrapolate. So you can give them a signal, half of the signal is missing, and they can still tell you what it is because they extrapolate. They fill in the gaps. And that's not something a machine can do today. So hopefully by better understanding how humans produce and perceive speech, and if we have a hybrid approach, so we don't drop the statistics, I'm all for statistical learning and machine learning, but we need to have a hybrid approach. We need to also understand what's important to train these systems. Then we'll have more robust systems. Since many of you in the medical field, it's like an FDA trial. And medicine may work for 95% of the people, but there's always 5% that the medicine doesn't work for, and therefore you have to individualize it. Same thing in speech recognition. It may work on X% of people, but there's always a segment which it will not work for unless we individualize it to find details in the signal. So with that, I'll end my talk and some other projects we're doing. And again, you can feel free to visit us on our website and download any papers. Thank you.